Okay, so hello everybody. Good at the meetup. Thank you for coming. We are going to talk about concurrency in an advanced architecture today. And in order to start, let me introduce myself. My name is Jorge Ortiz, and I do consultancy and training about architecture and best practices for companies that want to improve how their applications are built. And as part of this, I usually get asked for advice on how to implement concurrency inside of the applications. And this is what I plan to share with you today, this afternoon. So this is the agenda that I have set up. We will start by having some principles about the architecture, introducing what a reference model for an advanced architecture, the one that among many that can be used. And then I will talk about different options in order to implement concurrency, from the most simple to the most advanced and probably the most complicated ones. And then I will extract a few rules in order to implement this concurrency in your applications when using an advanced application. And finally, I will do a very brief recap. So these are the plans, and let's start with a very brief introduction to what I mean by an advanced architecture. And the first thing that I would like to agree on is that advanced architecture is not just one thing. It's whatever it fits your needs. Something that doesn't get in the way when you are trying to solve your problems and create your application. That is the most important quality of an architecture. But here, in order to start, instead of talking about abstract things, I would like to talk about something that is actual, that is real. I would like to introduce you to the clean architecture, which is a reference model that has been used very often, and that I also use as a reference in order to teach people how to implement advanced architectures. In this model, you have the architecture built around data and built around logic. The entities hold the data of the application, and the business cases, the use cases that you have there, the business logic that you want to hold, all this domain logic is contained in each one of the interactors that belong to the center of the architecture. The rest of it is just implementation details. So your business logic will try to be as independent as possible from whatever persistence you use and whichever method you use to display the data or to interact with the user. This is what you get from an advanced architecture. And this is denoted here by the yellow arrow that is the dependency rule. The dependency rule tells you that an outer layer will be able to know about all the details of the inner layers, while the inner layers should not know about the details of the outer layers. And probably, if you have already implemented even a few applications, you probably will be asking yourself, if you have never done this, well, I mean, I need communication to the data, but also I need the communication back from the use cases with their answers, with whatever information comes from them. So the way you do that is by using the dependency inversion principle. The dependency inversion principle is the one that tells us that our high-level code should not depend on low-level code. Our use case should not depend on the way we access persistence. Okay? So instead of that, we will create an abstraction that we will define in order to contain the methods that we are going to use to interact with the persistence or to interact with the views. And we will make our high-level code, our business cases, for example, our use cases, depend on this abstraction. And we will also implement the glue code, the one that is needed, in order to make our low-level code implement that abstraction. In that way, we will revert the dependencies. We will not be dependent on low-level code, on the way our persistence or our views are implemented. Okay, So this is how it is organized, and let me show you a picture of how this works through the different views that you have. This would be the view that this represents the view that you have in your application, and by the view I mean the view controller in the case of iOS, or an activity we would be talking about Android. In this view, we'll have all the views that are present for the user to to show information or to interact with. But these views should be as dumb as possible. And in order to provide them with all the pieces that are needed in order to have the kind of architecture that I was mentioning, we will be using a connector that will take care of all the injection in the view. So the connector will provide a presenter that will be responsible for providing the semantics to all the events in the view, and also responsible for telling the view what to do. I'm like, do I want you to put this text on that label, to change that color, to enable that button? The presenter itself is providing the semantics, but the business logics are not in the presenter. As I said before, they belong to the interactor, to the use cases. So in order to be able to have use cases when we need them, we create a use case factory that is injected into the presenter. And that use case factory is the one responsible for providing us with use cases as we need them. So when we create that use case factory, we also inject into the use case factory a reference to the repository, the persistence that we are going to use, which is referenced here as the entity gateway. Okay, so we have all the pieces. Now, if I want to run anything in my application, if the user taps on something that I wanted to be translated into show me this list, or into add this new bit of data to the database, or to delete something from the database, it will be done in a use case, and that use case will be interacting with entity gateways, and it will be commanded by the presenter. Okay? So, now that you have a very rough picture of what the architecture would be, let's talk about asynchronicity, sorry. And as you can see, I have added a lot of pictures here that come from, I have borrowed from science fiction movies. And this comes from The Contacts. And The Contact was a movie where she did a time travel, but the travel that she did to another star happened almost instantly. And this is what we expect from our code. We expect from our code to avoid any waits. The user shouldn't be waiting for the results of an invocation to the database or something that is computationally expensive taking place. That is why we want our code to run asynchronously. So there are two typical places where we could have this kind of asynchronicity. One is when we are invoking these methods, these interactions with the database. And the other one is when we are going to perform things that are CPU intensive. There are many more, but these are the two ones that you will find more often in most common applications. Obviously, there's a third one that belongs to the two categories. So I make an invocation of a backend API, and I also need to do some local processing, adding some intelligence to the answer locally. So where do I do this operation? Where do I start the asynchronous behavior? In the case of an invocation to the backend, well, it would be better if since I have an entity gateway which is abstracting all the interaction with the database, with the persistence, or with the backend, it is there the right place to add these asynchronous calls. From the perspective of the rest of the application, we will have an API that interacts with this backend that will be invoked and that will receive the information afterwards when the information is ready. Either the information or the confirmation that the operation has taken place. In the case of things that require a more intensive work from the CPU, local work, then we will need to have use cases that run asynchronously. And I'm going to cover both the scenarios with different solutions. So let's start with options. And in life, we have many options. So my plan here is to start with the most simple one, something that probably you have all of you have done at least once in order to create an initial call that is asynchronous, but that has some lackings, some things that could be better. I will start by introducing the idea. I will show you a few snippets of code. Then I will show you a diagram of how it works, and finally the goods and bads of that solution. So I will do that for a few solutions that I want to share with you here. Let me start with the most naive solution, as I said, and that is going to be one that we use the presenters to receive the data. And in order to do that, we define a protocol that contains at least one method, and that method is the one that is going to be used in order to invoke back the presenter with the data. I call the use case gets a reference to the presenter implements the protocol, and the data flows back to the presenter. The presenter has all the access to its own properties, and that means that it is very easy to talk to all the methods or to all the properties of the presenter and modify them as needed as a result of the invocation of the use case. So let's see a snippet of code here. Here, I have what is the protocol that I'm going to use in the presenter, which defines just one method. In this case, the invocation to the use case is going to return an integer. This is for simplicity. Could be any kind of data that you wish, but in this case, it's an integer. And here I have a use case. The use case has all the logic inside of this execute method that you have over here. And what I'm going to do is pass from the presenter to the use case a reference to the presenter that is implementing that protocol. And here, when I use when I get the information back from the database, from the persistence, I do an invocation to the method that I got through this call, through the call to the execute. Okay? So what happens then? Well, this is the presenter that uses this guy. Here in the presenter, I have declared this method that is the one that is responsible for dealing with the data when it comes back from it. Notice that this is the variable that will hold the use case, and I get the use case from the factory, and I execute it immediately. Since this variable here, if I declare the variable here locally, it would go out of scope, and the use case would be released. So I need to keep an instance variable in the presenter for the use case and free it after the call has happened. This is the simplest scenario. There's nothing simpler than that. And the reason why it's simple is because memory management is also very simple here. So we have the view, we have the presenter, and we have the use case factory. Notice that in these diagrams, the solid lines are strong references, while the dotted lines are weak references. As you all know, if you have a cycle of strong reference, you have a memory leak. And this is something that we would like to try to avoid. So this is how it would work. We are receiving some event from the view. The presenter provides the semantic to the event, and that means that it's going to run a use case that will run asynchronously. So in the presenter, we have implemented the protocol that defines the callback, and in the presenter tells the use case factory to create a new instance of a use case. Okay, so the presenter will keep a reference to the use case in this property, and in order to avoid having a memory leak, we will reference back to the presenter with a weak reference. Okay? That's it. That's very simple. So when we finish with the process, we will free the use case, the reference to the use case, and everything will go away. As I said, this is the simplest solution. It is very simple to implement. And memory management is trivial. The only thing that you have to worry about is to keep a weak reference back to the presenter. But it has several limitations. The use case should be retained, as we saw, because otherwise, when it goes out of scope, it will be released, and we don't want that. And we have an additional limitation, which is a strong one in most cases, that since you are implementing a method of a protocol, you are limited to have one method with that signature in the same presenter. So if you have two use cases that are going to use the same callback, you cannot do that. You can do things like what you have with the delegates, that you pass a reference to the object that created that in order to differentiate with the same callback. Second option would be using Lambdas, which in the world of Swift are called closures. So by a closure, I mean an anonymous function that captures the context. In this case, we are going to pass a closure into the use case, and that closure is going to be used when the use case has finished its job. So what we are doing is called continuation passing style, because instead of receiving the result from the use case, we pass to the use case the closure that we want to be executed, and that closure will take as the argument the piece of data that it returns from the use case. This is a snippet of code, and notice that in the first line, I'm defining what this general shape of these closures. So it's going to be a handler. It's generic because we are going to allow any kind of type there. It could be an integer. It could be a piece of data, a struct, or it could be a list of structs, for example. Okay? And I'm going to use that in one of the parameters of the use case when it gets created. This handler is passed on to the use case, and it is retained there. Since it's going to be used outside of the scope of this init method, I need it to be escaping. Okay? And when we execute the use case, when we get the data back, we will need to do a call to the handler which we got when the use case was created. Pretty easy. The nice thing here is that when you have defined the use case in the presenter, it is easier to see what is going to happen as a result of the invocation of that use case. I create the use case and I say, and when the data is ready, I want this to happen. So it is far more readable from my perspective than the other thing that was taking the flow to a different method in the same class, but to a different method of the same object. Okay, so this is how it works with Lambdas. We have the view, the presenter, the use case, as we did before, and we create a closure that is the one that we are going to use in order to create an instance of the use case. So the use case factory is provided with the closure, and it creates a new use case. It passes that closure to the use case, and from the presenter, we have to make a strong reference to the use case, and from the use case, we keep a strong reference to the closure. Notice that we, from the closure, are going to be captured in the context in order to invoke other methods of the presenter or to change some properties of the presenter. We don't want this to become a memory leak, so the reference back from the closure to the presenter has to be weak. That's it. As simple as that. So, as I said, far more readable. Memory management requires a little bit more of care. I think it's easier to see it when you have objects that when you put closures in the game, but still understandable. And the good thing here is that I can use closures on demand. I mean, I can create any closure at a given time to deal with the data as long as it matches the signature that I have set. And still, we have to retain the use case till we finish the execution, as we did before, which is a drawback, obviously. The next option would be to use a more advanced retaining, but based only on GCD. And GCD, well, probably all of you are aware of this manifesto that Chris Ladner wrote about concurrency and how to implement it in Swift. And even though we haven't been genetically enhanced as the guys in Gattaca, we are able to prove that we can do our job without all these additional methods to provide concurrency. So let's show how this happens. The asynchronicity in this case is going to happen at the level of the use case. It can also happen at the level of the persistence, but we will be able to have asynchronicity in the use case. We are going to use here composition versus inheritance. So I'm going to composite a class that is able to take the asynchronicity capabilities into a use case. And we are going to, as we did before, use a closure in order to define what is going to happen with the result. So this is a snippet of code, and I define another protocol that I will be implemented in each of the use cases that I want to be asynchronous. So this protocol that we have here has an additional method, and which is async execute, and a reference to a queue. That's it. So this extension, this protocol extension that I use, takes care of using the execute method that I use normally in a use case and invoking the async execute in a closure and send it to the queue. It uses GCD in order to capture itself and pass it on to a queue. Okay, so notice that here I have a reference to self, and because I'm not using a weak self here, this reference is strong. I'm keeping a reference to the object in the closure that is strong. So when I use it from the use case, I will have this method instead of the normal one that was the execute. It requires changing a little bit the structure of a use case, and the way it works is exactly as we did before. We have the view, the presenter, and the use case factory, and we provide a use case factory with a dispatch queue. So I will have a strong reference to the dispatch queue, and in order to create a new use case, I will create a closure that I want it to run. The use case is going to be invoked by the use case, pass by the use case factory onto the use case, and I have a weak reference there, strong reference in the closure, and I have a weak reference to the dispatch queue locally in my use case. So when I dispatch myself, when I send the use case to the dispatch queue, I can have a strong reference without having a memory leak, and I create a weak reference to the presenter. Okay, so when this goes away, I still have a strong reference all around in order to have this without a memory leak. Again, I can have as many closures here as I wish. I can avoid having a retention of the memory of the use case. So I can run and forget, and it will be held by the queue as long as it's needed. And not all, but most of the behavior that we want from the use case that is asynchronous is abstracted away by the protocol extension that I showed to you. The thing is that the structure of a use case is slightly modified. Instead of having a function that does the execution, we have a function that does the asynchronous execution. And the memory management is a little bit more complex than what we had before. But operations come to the rescue. And let's see how to do this with what we used to call NS operations that are now plain operations in Swift. So the asynchronicity is going to be still implemented in the use case. I'm going to use inheritance instead of composition because we are going to inherit from an operation in order to take advantage of the abilities. And we are going to, as we did before, use a closure in order to define what to do with the result. So this is an operation use case, which is a subclass of the operation that will hold the thing for a use case. In the execution method, we are going to run the queuing of our job in the operation queue. And in the in each of the use case, we have a weak reference to the operation queue, so we can use it in order to do the queuing. As for the use case, well, everything will take place in the start method instead of the execute method, because that is the method that is used by operations in order to run whatever is asynchronous, okay? And it uses this ability that is part of the operations to cancel itself in case the user wants to do so. So we have additional abilities. Not only that, we also can create dependencies in our use cases. So if we want to run one, only one, another one has finished, that can be done with these operations. So this is how it would work, very similar to the previous case. Instead of a dispatch queue, we would have an operation queue that is connected to the use case factory. And in order to create a new use case, we define a use case closure, and we create the use case from the use case factory. The closure is then passed on to the use case, and then we have a temporary reference, the one that is in scope, and the closure will be held by the use case. The use case, as I mentioned before, it has a weak reference to the operation queue, and when we queue ourselves as another operation to be done, we have a strong reference from the operation queue. So when this goes out of scope, then we have this reference go away, and our closure will be still connected to the presenter. Okay? We can have here as many closures as we want, as we had before. No need to retain the use case, which is, as we said before, an advantage, but also we have the ability to cancel and to create dependencies between the different parts of our use cases in order to provide a more coordinated solution. The thing is that we also need to modify a little bit the structure of a use case, and the memory management is as complicated as in the previous case. Let me show you another alternative, features. Has anybody here used features? Yeah? Okay. So for those who have, probably you have already seen the power. For those who don't, a feature is a very powerful abstraction because it allows you to put into a box, a feature, an operation that is going to be computationally expensive. So what you do is I define something that it will take some time to be done, and eventually the result will be there. But I don't want to worry about the process. I just want it to take place asynchronously. So that is what we have in a feature. The features, by the way, are monads, and that is very powerful in most implementations because there are several implementations in Swift. And the thing is that the reason why we have several implementations in Swift is because it doesn't come as a given in the standard library. The one that I use is the Bright Features, which I believe is the most advanced library for that. But as I said, this is not part of the standard library. So what do you do in a feature? Well, in a feature, you have the ability to define your reference, your methods, in a way that instead of calling back things by using the continuation passing style, they immediately return something that is the feature. That doesn't mean that the computation has been finished. That means that it provides you with something that when the computation has finished, it will give you the data. Okay? So what we do here is we can immediately use the result of that feature, and we can deal with it using transformations that come from functional programming, which is really powerful. So we use flat maps in order to have dependencies. So if I have a successful result of whatever comes from the persistence, I will execute the transformation into another feature that is the result of multiplying by 2 the previous one. Very cool and very powerful. It requires a little bit of functional programming knowledge. And from the perspective of the presenter, we still have to use continuation passing style in order to avoid having different return types from the presenter and dealing with them homogeneously in a way that allows us to have a proper use case factory. So what we do is we get the data through the continuation passing style, and we still can manipulate this data functionally. How they work? Well, so Same thing as before, we define a closure, we pass it on to the use case factory in order to create a use case, the use case is created, and that closure is then passed on to the use case. Immediately, the result of the complex computation is returned in a future, and notice that these two references here are scope reference. So when I get out of scope, they will be released. The closure then has a reference to the presenter that will do the changes, and is passed on to the future in order to execute it when required, when the computation has finished. So what do? We finish the scope, and then the reference, we keep the reference to the future from the presenter, and when the scope finishes, the reference to the use case disappears. With it disappears the reference to the use case, but even that reference to the future has disappeared. The future is still there because it's held by the presenter. That's that easy, okay? So this is a very powerful abstraction. I like it a lot. I would like it to be part of the standard of what is offered by the standard library, but it is not there yet. The purpose of the Bright Futures developers is that it is copied into the standard library of Swift. I hope they are successful at that. But not only that, I mean, like using this feature, we have proper error propagation. The result of a feature is either successful or not, and that helps us propagate asynchronously errors to higher layers and be aware of whatever has happened at a lower layer and transform it as we need it. So, as I said before, we can use functional programming in order to deal with this transformation, not only with the transformation of the good results, the successful ones, but also to transform anything that is an error that is coming from a lower layer. And as I said, the only problem is that it's not part of the standard library. Reactive. And for those who have seen The Arrival, you will see the similitude of what I'm talking about. So I'm trying to understand the language of these aliens with this reactive. And reactive is like an Uber future. Instead of just having one computation that will give me a result or an error, I have a sequence of things that can come that is a computation, but can provide me not just one, but many results in a row. And I can have, every time I can have either an error, an event, a result, or a completion saying that the sequence has finished. So dealing with this at a higher level as a first-class citizen in the architecture is what we do with Rx. How does it work? Exactly the same as futures. So we define the closure, we pass it on to the use case factory, and then we have the use case created by the use case factory. When we want to execute it, we have passed already the closure to it, and we have a local reference to the use case. Then we create an observable. Observable is the way we deal with these streams of results in the Rx world. And this observable is provided with the closure in order to subscribe to it and deal with it. So the closure has a weak reference to the presenter, so we don't have a memory leak, and we hold from the presenter the observable that has been returned by our use case. When we get out of the scope and the local reference to the use case is finished, then our use case can be freed, and still our observable will be emitting data as needed. The advantage that it has over the feature that I was mentioning before is that this is not limited to a one-time result. It can be something that is going on through time. Okay? So the highlights of this solution is, well, as I said, this Rx is very powerful. It requires an initial investment in order to understand how the pieces work together, but it is quite powerful in the sense of being able to provide us with transformations that can be applied in order to modify the different observables, the results from the different observables that we use in our application. But it comes with a lot of operators out of the box. So there are many that can be done by default, that we don't have to worry about how to do the transformations. The same mechanism can be used in order to notify, for example, changes in the model to the presenter. And that is quite powerful, because instead of having to use two different mechanisms in order to transmit these changes, I'm using the same one that I'm using when the results come from a use case. This one is also not part of the standard library of Swift. However, I would say that this is fairly standard. There is a reactive XIO site that has a consistent implementation for most languages, and I would say that this is fairly standard. Even though it is not accepted as part of the language, you wouldn't have a lot of problems by going to a different project and using the same kind of code. What I have provided you with, all these solutions that I was mentioning here, were mostly early stage implementations of the different possibilities in order to have concurrency in your code when you are using an advanced architecture. So some of them, well, all of them can be tweaked, and your purpose should be that. I mean, not initially, but you should start from something that you understand and enhance its performance when needed. The thing here is that I would like to share with you a few rules on how to do that and how to apply the different solutions and what to do. And these are that, like anything else in terms of architecture, don't go with what is trendy. Probably, otherwise you are already doing RX and you don't understand why. That shouldn't be the case. Try to solve the problems that you have and try to understand what is the best tool in order to have the benefits that you're looking for in your application. That is the key on choosing something that is right for your architecture. And that means that once you have chosen a solution for that, you will have to follow the requirements of that solution. I mean, like whether you use queues or not, whether you have to directly address GCD, or if you have to deal with memory management in a given way, that is part of the solution that you have chosen to apply based on your requirements. But once you have chosen one, be consistent, because in my opinion, most of the bugs that come with concurrency solutions of most applications come from the fact that different developers, different members of the team, implement their concurrency in different ways. And that shouldn't be the case. You should integrate the way you perform concurrency in your code review practices. You should ensure that you have agreed upon the team on how to do proper concurrency implementation, and then everybody will have to accept that decision and apply it accordingly to all the parts of the application. And you can obviously use functional programming in order to take advantage a little bit farther from the things that we mentioned before. So the final takeaways, and I think that are quite obvious based on what I was mentioning before. Don't go for the fanciest, don't go for the trendy thing that everybody's doing, but choose a solution based on what you need. Can you deal with just having concurrency in the calls to the backend? If this is good enough for your application, don't go into something that is more complicated, that is going to be to make your application harder to read, harder to be understood by people that come new to the team. Instead, go with the simple solution that fits your needs. And when you have different approaches, you have to be consequent with the decisions that you have taken and implement them properly. It means that you should understand what are the quirks of having this approach implemented in your application. Particularly, memory management is a very relevant thing when we're talking about concurrency. And please choose one. As a maximum two, if you have two needs that are different. But I don't think that it should be the case that every different situation should be solved with a very different pattern in your application. That is not a great idea. Think it twice and choose one or as a maximum two solutions for your concurrency. So that was all I wanted to share with you, Tak. Thank you very much. And if you have any questions regarding what I have shared with you or anything that is related to architecture or any other topic that I may know how to answer, I would be glad to answer them. You can also ping me online. This is my Twitter handle. And I'm also very happy to answer people who send me any tweets. So thank you very much.